Time?
Testing. 1, 2.
So you, Josh, and the other guy.
Actually, I can lower it in here. Sorry.
No, just lowered it.
Zed.
I gotta do it.
Oh, unfortunately. You're still studying.
Okay, that's fine now.
You graduated
Testing.
this day?
1, 2, 3.
I'm joking, that's good.
Should be fine. Testing. Testing.
You're working so much.
It's pretty loud. Oh yeah, it's good. I'll check if it needs to be turned up. But you can.
And he's still failing at that as well. Oh, so record it again.
To control the camera.
MATLAB Carmen. Back up.
All right, thanks for coming, everyone. Hopefully the stream's all working all right. So this is our second last event for the year. Thanks for coming along. I know it's week 13, but I'm sure we'll have some good stuff ahead of us anyway. Without further ado, here's Vedant here to tell us a bit about SiMpLE.
Cool, thanks Quinn. Thanks everyone for coming down today. I know it's week 13, it's a busy time. My name's Vedant. I'm a PhD student under Tyson and Ross. And this is just presenting some of the work that we've been doing over the past year, and it's progressing on to something that's good. So without going into details too much, let's get started with a simple scenario. So we've got an environment, okay? Well, I'll put some houses up as well, and some nuclear reactors, among other things. And we've got a start point and an end point. Point A, point B, got a vehicle. I want to start at point A, and I want to get down to point B. Obviously autonomously. Well, let's say, just to begin with, I've got a person in there. For a person, this task is quite simple, all right? They know what the path is. They've got their own perception systems built in. They've got a cognitive ability as well. And they can go ahead and say, you know, I'm here at this location and follow a well-known path. What happens when we remove that person? So for an autonomous vehicle itself, it's got many subsystems it needs to know about. It needs to plan a path. It needs to avoid obstacles in its path. It needs to know its current location. Let's go ahead and just reduce this problem really down. We're going to assume we've got no obstacles in the way. We're going to assume we've got a perfect map of the world, and we know exactly how to get from point A to point B. What's the one thing that we still need to know? That's where you are at every single point. So whether I'm down the track, whether I'm turning. So it's just that essential capability that the agent really needs to know its own pose or position and orientation at every step of the way. The most common solution to this is to use GNSS. You know, GPS satellites tell me where I am at every single location. And it's very precise, it's highly accurate and reliable. But what happens if we lose that? So I get a highly vegetation area, or I lose my corrections, and I lose my pose information. Should the car just stop? How should it behave? If it doesn't know where it is at any single point, how can it go on and progress its path? Okay? And this is where this line of work really starts coming in. What do you do in the absence of GNSS, or in areas where you don't have GNSS? We go down to an underground mine operation, you're not getting any GNSS signal there. How do you continue to form that ability to know your position in all these different scenarios? And once again, this is a huge problem for autonomous robotics in general, whether it be the autonomous cars that are currently roaming all over America. You've got drones that are set to go on some fixed flight paths. They need to know where they are so they can follow a path. Agriculture is following this as well. And you've got the same implementation in mining robotics as well. They all need to know where the position of their vehicle or whatever agent they're looking at is at any one point. And this is commonly known as the where am I problem. Now, it's a requirement for all autonomous agents, or most autonomous agents, to know their position relative to some reference. Now, this reference can be arbitrarily chosen, but what's important is that the agent needs to know where it is at any given time step. And from our example before, you know, a car needs to know its own position at every time because it wants to update its path to get to its destination. Now, most importantly, answering this question is a prerequisite for subsequent actions, such as decision making. To make a decision autonomously, I need to have a belief of the world, and that belief is provided by these systems. More commonly, this problem is known as localization, and it's just as important for machines as it is for humans. When we go out somewhere, we always localize within our environment, so we know where we are. When you walked here, you followed some sort of known map and localized yourself within it so you know where you were going. If we want machines to perform autonomously, they need to be able to do the same functionality. The first question that always gets raised is, what do you do, or why can't you just use GNSS? And we talked previously about, it becomes unreliable sometimes, but GNSS provides centimeter accuracy, and it's really great given these two things exist. So one, the GNSS receiver has a clear line of sight to sufficient satellites. Now that's great in an open area. You go into the CBD where there's an urban canyon and you lose satellites. What do you do then? Do you just restrict autonomous vehicles from operating within the city? Most likely not. And your second requirement is that you require RTK, or real-time kinematic corrections. Now, RTK correction is required to get that accuracy down from a meter to sub-centimeter level. Now, without RTK or sufficient satellites, you lose that accuracy and go, okay, I need some other solution. And GNSS is being continuously improved. You've got better receivers, you've got more improved clock accuracies, and there's also more alternative options such as network-based systems such as LiDAR that are being introduced to overcome these problems. But there's still a solution that's needed that uses onboard sensor systems. So the simple question we're answering today is, what do we do in GPS-denied areas, such as tunnels or indoor environments, or situations where we have GNSS, but it's just not reliable enough to have 24/7 autonomous operation? And this is where this huge field of study called Simultaneous Localisation and Mapping, also known as SLAM, really comes in. And it's a large and expanding area of research still on how we can use observations of the environment to understand the agent's current location. Now, approaches to this problem are broken down into two main parts. And the first part is, how do you interpret the environment? That's where your sensors come in. Now, sensors are wonderful. We've got all different types of sensors. Most commonly, you'll see cameras or laser scanners, and that's what we're going to be talking about today. But they only give us so much. They only give us a pixel value or a range measurement. The second part of the problem is all about how we interpret that information. And that's where all these algorithms come into play. So the first part of the problem is to, one, get some sensor data. But what we're looking at today is how you go ahead and interpret that sensor data so you can go ahead and make beliefs about the environment. Now, I've got front end and back end there. We'll go on to an example in a second. But essentially, your front end is all recursive pose estimation. Now, all we're meaning by that is sensor data comes in, and we make a belief based on that sensor data. Back end is when we can use some history of sensor data to make a more informed decision. And most commonly, we have to use both of these if we want real-time and accurate results. For what we're going to talk about today, we're going to be focusing on that front end part, which is all about taking in sensor data at time K and forming that belief straight away. We're not going to be using the history or doing some batch optimization at all. So just want to make clear what I was talking about. So at some point, we're going to initialize our position. Let's say this is the origin. I'll have some sensor data come in. At the next time step, we'll have some new sensor data come in. Now, based on those two sets of data, I want to go ahead and update what my position is. So that T is a transform, pretty much saying how much have I moved from the first, so P0 to P1. In a 3D environment, that's a 6-degree of freedom problem. I've got my X, Y, Z that I can move in, and I've got roll, pitch, yaw that I can also move in. And we do this over and over again. So new sensor data comes in. Based on my initial position, so P1 now, I can go ahead and estimate what P2 is going to be. And that's what recursive pose estimation is. New sensor data comes in, and I estimate where I am right now. Now, batch estimation is different because that's going to go ahead and use all those estimates or the estimates within some window to go ahead and determine what the pose estimates are. Because one of the problems we see straight away with recursive pose estimation is if a single one of these estimates messes up, the subsequent pose estimates also mess up. And that's a huge problem. Sometimes maybe your algorithm fails, your sensor data doesn't provide you with the correct representation, and you use that and get an incorrect belief and build off that. And that's where batch estimation comes in, where it tries to smooth and try to identify, something wasn't right here, let's either ignore that result or fuse that result with something else. So batch estimation is really powerful, but once again, the batch estimation or back-end methods rely on having a good front end. If your front end can't provide accurate pose estimates, your back end won't perform well either. So it's more like a prerequisite for it. Okay? Now, we talked about, before we get to the interpreting stage, we need some form of actually getting some sensor data. And the whole goal here is we want some representation of the environment. We talked about cameras, we talked about LiDARs. So LiDARs is what we're going to be using today in our talk, mostly. Now, cameras and light imaging and detection ranging, or LiDAR, are typically used, like I said, and there's pros and cons of both. Okay? With RGB images, we get color information. We can perhaps make a more better understanding of what the world actually looks like. However, with LiDAR, we get a more accurate representation of the world, at least with the geometric features. And to be honest, some of the best algorithms out there rely on both of these. They somehow fuse the information together to get the best belief of the world. Now, LiDAR sensors in general, they come in all shapes and sizes. Over the past 10 years, there's been a rapid development in all different types of LiDAR. They've got varying fields of view, the number of beams they've got, the point cloud density they're dealing with, the minimum and maximum ranges they've got. So just as an example here, this RoboSense SiMpLE, it's got a hemisphere. It sees half the world, whereas the Velodyne has some vertical field of view limits. And it still sees 360 degrees, whereas the RoboSense only sees the front half. And that all impacts on what representation you get. Now, the reason I'm going through these is because if we want to develop an algorithm that works with point cloud data, so data coming from a LiDAR, we want it to be agnostic to that algorithm. To that LiDAR. We want it to work in all these different scenarios. You don't want 10 different algorithms for 10 different LiDARs. So having a look at what a typical LiDAR output actually looks like. So understanding what a LiDAR output is, so a LiDAR returns a set of range measurements at specified heading and bearing angles. So that's in spherical coordinates. And they can be very easily converted to Cartesian coordinates. So what we've got here is just a plot of individual points. What it also includes is metadata. And this obviously changes per sensor, but this includes stuff such as your intensity of each point, and some newer sensors which are including per point velocity, or the number of returns you've got on each point. But at its very, very basic level, all we've got is Cartesian points. And we somehow need to use this to build a belief of the environment and where we are currently. So let's have an example of a quick video here. We've got a LiDAR that's attached on top of a vehicle, so rigidly mounted. That vehicle is driving around, and this is what the LiDAR is seeing. Okay? It's not making any interpretation. This is just raw point cloud data. Now, as humans, we've got great cognitive ability and pattern recognition, and we can start seeing, oh, look, there's a car there, there's a bus there, and we can say, okay, we're going pretty quick. If we turn, we can kind of see that. But to a computer who's only seeing this as X, Y, Z points, and perhaps 100,000 of these per scan rates at 10 hertz, it's a lot of data it needs to build beliefs from. How do you go ahead and answer the question where you are right now? Yeah, that's what we're trying to answer. How can we use this data to do that? So let's go through a very simple example. There we go. Let's say I got 2 scans. So this is using the same data you just saw. So I got a scan at t equals 0.1 seconds. Like I said, these scans depend on the LiDAR I'm using. This is a scan from a Velodyne HDL64, approximately 100,000 points per scan at 10 hertz. So I get the scan at t equals 0.1 seconds, and I've got my sensor frame here. So that's just the origin of the sensor. At t equals 0.2 seconds, I get a second scan. And we can see, most of the scan is the exact same. What we're really trying to find out is, have I moved based on this observation? Well, what is really going to help me is static observations, or static parts in that observation. So we've got some edges or some features here, which are also coming up in this scan. We've got the road, which is shown to be flat. But if I was to go ahead and overlay each of these scans on top of each other, we can see that they're not the exact same scan. In the sensor origin, these geometric features have shifted, and stuff doesn't really line up. We've got some angle offset here. This should ideally be lining up with this. So what this is really showing us is that the sensors moved within these two scans. So if I started to move around the second scan on top of the first scan, so adding in a bit of rotation, I can start lining stuff up. And I also moved this in the x-axis or horizontally and tried closing that gap. And you can start saying that when I do that properly, I can estimate how much I've moved. So by registering or matching these features, or points in this case, I can say, oh, that's where I was before, and this is where I am right now. And this is the foundation of these ideas, is based on these observations, I can go ahead and say, I've moved this much. And this isn't 6 degrees of freedom. So I have moved in X, Y, Z, and I've rotated in roll, pitch, yaw. And that's the entire underlying theory we've got there. This allows us to determine how much platforms moved within the time step between the two scans. So if my scans are coming in at 10 hertz or 0.1 seconds, I can say I've moved this much in 10 hertz, in 0.1 seconds. And doing this recursively, so that recursive pose estimation is coming up again, I can go ahead and try to, one, build a trajectory of where the sensor's been. And if that sensor is mounted rigidly to a vehicle, you know where the vehicle's been. And two, you can try to build a map of the environment which has many potential users. Okay? So this is the general approach to pretty much nearly all the algorithms out there. There's two parts to it. One is an objective function, and it's a fancy way of saying, or having a quantitative score for how well the two scans fit. When we looked at the examples earlier, we knew that the original scan didn't really fit well. And this was just more qualitative. We were like, okay, stuff isn't lining up here. But when we tried fitting stuff together, we go, okay, that's fit well. That's our error metric, or that's our objective function for how well two scans actually fit. The second part to this is what we were doing in 2 steps. A pose search algorithm. How do I find what those magical that magical transform is that moves one scan on top of another scan? And in terms of a 3D case like ours, that's those 6 parameters. So roll, pitch, yaw, and X, Y, Z. How do I find what those values are? Now, one approach that comes up straight to mind is, why don't I just test every single possible approach within some window? So why don't I do a brute force on all the possible angles and all the possible translations? In a 6-DOF space, that adds up very, very quickly. And now we go back to one of the requirements, which is we want real-time pose. How do you search for all those poses? And maybe in the future there's a computer that's fast enough, but currently it's not a feasible approach, because that goes very, very quickly. And what we require is some sort of pose search algorithm or optimization algorithms that go ahead and find what the best pose is that fits or that achieves that objective function. Now, the most popular approach is from the 1990s, and you'll be surprised at how prevalent it is still today. It's called the iterative closest point algorithm. And it's a very, very simple approach, and it's kind of what we were doing in the previous step. So over here, when we were comparing these two scans, we were trying to find, or we were pretty much examining the error between these features, right? We were going, oh, where do we minimize this error between these different features? And that's essentially what the iterative closest point algorithm is. It's trying to minimize the error between features and find what the best pose that provides that is. It's got 6 steps: selection, matching, weighting, rejecting, calculating an error-based metric, so that's what we're talking about, and minimizing that error metric, so that optimization or search algorithm. Now, it works really well given perfect data. And what we know from the real world is real data is noisy, and it has dynamic objects. So on that error-based metric, we're assuming a static scene. Okay? If I had a vehicle in one of my scans, or many vehicles if I'm traveling on a highway or in an urban environment, and stuff moved, trying to minimize the error between point clouds won't get us too far. We'll have error build up. And that's where this algorithm breaks down. However, to counteract all those problems, whether it be noise or dynamic elements or speed even, there's been an increasing number of variants of this algorithm. So that plot there is just showing, it was originally published in 1992, and until I think this plot was made 2022, it's still growing and exponentially growing with the number of people that are making variants on this algorithm just to overcome the limitations. And it's been studied, so this problem in general has been studied for the past 40 years, but we're still producing new solutions. And there's a few reasons why that's actually happening. One is approaches are tailored to a use case. Many of the early algorithms that were developed were all indoor-based and with 2D LiDARs. You tried to do the same algorithm outside and it broke because it wasn't a static scene. And that's still the case today. Most of the algorithms out there will work in very specific environments very, very well, but you try porting it to a different application and it breaks. And that's not what we want to do. We want something that's robust. Majority of the solutions are based on the iterative closest point algorithm, so ICP, and we talk about why that's a problem. And the third thing is we've got huge development in sensing technology. Going back to 1990, there were only 2D LiDAR scanners. Coming back to 2013, we've got 3D LiDAR scanners, giving us much more information about the world. And now we've got even more information. We've got per point velocity that can be used to improve these algorithms. Just having a quick look at what actually exists out there. So you've got state-of-the-art algorithms, and once again, these work really well for the environments they're designed for. However, the simple problem is they've got up to 107 configuration parameters. Going through and finding the permutation that works best is hard. If your application doesn't work straight out of the box, you're going to have to go and tune those parameters. And we've got here, so they are using postgraph optimization, so that's the back end along with the front end. They're extracting all these features, so through normals and point cloud properties, all in the aim to go ahead and find how much the vehicle or whatever platform they're on has moved between two time steps. Second example, so once again a very popular algorithm, but the same problem occurs. You've got multiple steps, you've got 49 configuration parameters, and just the permutations you have to go through to find something that works is painful. And that's not what you want out of a good algorithm. A third example, so once again, this is a very popular algorithm where they're going ahead, converting it from a spherical coordinate frame to a range image. They're segmenting out different parts. What we see is at the center of all these algorithms is the ICP algorithm. So once again, they're improving on this very basic algorithm to overcome its limitations. And I really just wanted to put this one in. I know there's no pictures on the slide, but KITTI ICP was released last year, and if it is something you're interested in to getting into, they've got an amazing software package that works really well, but the same problem occurs. Yes, they're building an ICP, but they have taken a simpler approach, and that is what that's what they're advertising and going off. That's what their motivation was. And it is simpler, but there's still many intermediate steps, such as correspondence estimation, adaptive thresholding, outlier rejection, parts that are more heuristic and aren't very simple to understand. So just have a quick break there. We've gone through the problem of what we're trying to do. We've gone through the theory, or at a very high level, of what the current approaches use. We've understood what a LiDAR is, what the outputs of it are. And yes, it is very pretty, but it's always much harder to make sense of that information. We're trying to interpret what's actually happening. Gone through some of the state-of-the-art approaches and the gaps that exist. So we still want some algorithm that works out of the box, in different environments, with different sensors, and on different platforms. And that's what we've been working on here. So our approach, it's called SiMpLE, for simple mapping and localization estimation. And it's called SiMpLE because it's simple. We've got 3 steps and with 4 configuration parameters. And we're going to walk through the steps and, more excitingly, the results in a second. But essentially, out of the 4 configuration parameters we've got, so already we're down from 49 and 107, so significantly less permutations. Of those 4 configuration parameters, 2 of them are purely for computational benefit, and one of them's a convergence tolerance. So only really one of the parameters is left to make a significant impact on how the algorithm runs. So the first step is to spatially subsample that scan. Like I said earlier, some of the scans that we're getting in are up to 100,000 points per scan, and that's coming in at 10 hertz. So to try and do that at real-time speeds is always going to be hard, especially when you're doing it on embedded hardware that's normally on robots or autonomous platforms. So your input scan, we go ahead and subsample that at some value RNU. It's 0.1 meter. We're just spatially subsampling it, trying to retain most of the geometric information we can. That subsampled scan goes ahead and is registered or matched to that previous scan. And that's where that main difference happens in that matching algorithm. But before, we were using an error-based metric. What I'll show on the next slide is we replace that error-based metric, which is what's the error between these 2 points, to a reward-based metric, which is how likely is it that these 2 poses are aligned. And that makes a huge difference, which we'll see. And once we've registered the scan, found our pose estimate, we update a map, which is spatially subsampled, of some history of scans, and that's just used to maximize the overlap between that registration process. And it'll make a lot more sense when I show what's actually happening. But once again, 3 steps and 4 configuration parameters, which means we don't have any permutations, and it's much harder to break, and much easier to actually configure straight out of the box. So let's say we've got 2 scans essentially. The map is essentially a scan we've built up over time. So the existing map and a new scan. What we were doing previously was calculating an error. So this dij, we were just going, oh, what's the distance between this? And we'll go ahead and minimize that distance straight away. However, what we're doing now is we're actually going to reward this with a Gaussian function. What benefit this actually provides is when we have dynamic obstacles or parts that actually don't exist between both scans. If we've moved too far, I might not see this building again. Instead of trying to minimize that error that doesn't actually exist, and which would normally take some sort of outlier rejection scheme, we're just not going to reward it. So the points that don't contribute to the reward, they don't contribute to the pose solution we're looking at. And that simple idea is making that significant difference we're about to see in the results. And that sigma, so standard deviation for that Gaussian function, is just how much we want to reward. It's a tuning parameter, but it's very insensitive. So we had a look at the scans that we saw earlier. Now, using those simple ideas, if we go ahead and try to stitch those scans together, what do we actually get? So from stitching those scans sequentially, we can actually estimate our trajectory. So that red coordinate frame is our vehicle there. And at the top, we've got a map which is being built of the entire environment. So that's just building a map over time. There's no batch estimation. It's just recursive pose estimation. So driving across the road, we'll see some cars in a second. But this is scan-to-scan stitching. This is essentially what we're doing with the SiMpLE algorithm. So you can see there's cars crossing the road there, and the vehicle's waiting. So without any GNSS, we're able to answer that question of where am I for autonomous vehicles. And I'll let that finish. So we end up at the same position where we started. So we've got low drift over, I think it's 4,000 scans for this sequence, played at 2 times speed. And we end up with a final map, which we can use in a later application. Okay? And we go ahead and try and do that with a whole heap of different scenarios. We don't want this to work with a single sensor. So we've got a Velodyne VLB16, so down from 100,000 scans to 14,000 points per scan. That's at UQ. And I'm going to go in each of these data sets in a second. We've got a MulRan data set, so that's over in South Korea. Completely different sensor, still able to achieve the same accuracy. That's the data set we just saw. And this one down there is a handheld RoboSense BPL. We're going to go into that one, but essentially mapping a forest with a handheld sensor. So the platform is a human person. But the entire goal there is to demonstrate that it works with, 1, different sensors, and in different environments, and of platforms with different dynamics. What do we actually do differently that works and doesn't rely on ICP? So most of the modern approaches will rely on ICP, like we saw earlier, and the problem there, error-based metric. We don't want an error-based metric because we can't handle dynamic objects or when we've got minimal overlap. We essentially reformulate that problem from scratch, and instead of minimizing error, we maximize reward for points being close to each other. And this overcomes majority of the problems we're looking at. We don't need pre-processing or point cloud segmentation that's generally required in most of the ICP-based methods. We also don't need, so this work is currently under review in some journals, and we're just trying to we've got an open source implementation ready to go. Hopefully when that's passed through, it should be available. But in the meantime, like I said, the KISS ICP is absolutely wonderful. So I would highly recommend looking into that as well. To actually test how we performed, because obviously you can make an algorithm, you can say you're good, but you can't show that you're good until you've benchmarked. And there's no point in saying or giving this talk if we can't meet the same accuracy requirements as some of the existing algorithms. So to understand and evaluate our performance, we went ahead and tested these on various scenarios. One of them was benchmark datasets. And these are just datasets that all algorithms mainly use to show, okay, we get this % accuracy compared to a GNSS solution. Because that's the only ground truth we really have. We also did a dataset at UQ to investigate some of our own sensors. A haul truck in a mining environment, so that was an old dataset, but once again, it's just as usable now. And also a handheld LiDAR in a dense forest, just for a different application. So benchmark datasets, there's two main datasets that are commonly used. There's many more for various niche applications. One's a KITTI dataset, which is a set of 11 sequences. So this was released in 2013. Bit old, but still serves the purpose, consisting of 23,000 Velodyne HDL scans. So very dense scans that normally help in feature extraction-based methods. You've also got the MulRan dataset, which is a set of 12 sequences, consisting of 154,000 ouster scans. The main challenge with this one is that the ouster has a 70-degree blind spot for where it's mounted. And that makes it challenging because you don't get to see the entire environment when you're trying to stitch the scans. Benchmarking our performance against open source algorithms. So on the y-axis here, we've got the average translational error for both these data sets. Now, the lower the better. And on the x-axis, we've got the number of configuration parameters. Now, the whole motivation behind our work was obviously to make something agnostic, but also try to minimize the number of permutations of parameters you can actually have. So we perform quite well in the KITTI average dataset. KITTI dataset on the average translational error for the least number of parameters with very well performance. And we have the best performance in the MulRan dataset with, once again, the least number of parameters. Now, what's interesting to see is some of the state-of-the-art methods that we talked about before, such as MULs, performs really well on the KITTI dataset. But trying to port that same result over to a different dataset, which is quite dense scans as well, it performs quite badly. So it's got around 0.5% translational error up to 4.5 to 5% in the MulRan dataset. Now, unless you want to go ahead and try tuning those parameters more, this becomes quite a challenge. And that's the entire motivation behind the work. This was Tyson's car a few years ago. The dataset was originally recorded for some thesis students. I was an undergrad student as well then, but we were like, okay, we can surely use this data for what we're doing now. And the whole motivation behind using this set of data was most of the benchmark data sets tend to have very, very dense scans. We wanted to go in and see, okay, does the algorithm still work if we give it not dense scans? And that's where we picked two different sensors. So we had a Velodyne VLP16 compared to a Velodyne HDL64, and we had a Livox Horizon, just so we could get a completely different scan pattern and see if it still works. Now, we had a Novotel GPS solution, so we could compare how our algorithm performed. And we also had a KITTI, which is a commercially available SLAM solution to test how it performed. Now, looking at some of the results, so these are all around UQ. So the first one, we did a very simple couple of loops around the athletics area and the KITTI odometry. So we've got two sets of KITTI results. One's recursive or front-end poses estimation only, and the second is its SLAM solution. So it's front-end and back-end. And that's what it's really powerful at. And you can see even in the solution for the athletics area, it performs very well. However, when we go ahead and try to do a much longer sequence, consisting of 14,000 scans around UQ, using the Velodyne VLP16 data, the SiMpLE performs quite well with low drift, even though it's such a large data set. Whereas the KITTI actually breaks. So it performs really well for small sequences, but larger sequences it can't handle. to try with a different sensor, we tried with a Livox Horizon. So a completely different scan pattern. And we mapped out the path from here up to the guy at ferry terminal and back. And once again, it lines up very nicely with the GNSS solution. For a different use case, found a data set which the Smart Machines group had from 2013, where they mounted a set of sensors, including a GNSS solution and a Velodyne, on a haul truck. Now, very different dynamics, very different environment. And to examine how it went, so these are at 20 Hertz, so even faster, even though we only have half the data looking in front of us. Once again, we're able to map the solution, map the environment and form a trajectory once again. Now this is 4 times speed because the haul truck was very slow. But the main difference we're trying to illustrate here is we're not doing any feature extraction that other methods would fail on. So other methods that are looking for light poles, looking for the road, looking for buildings, they would fail in such an environment because that doesn't exist in this example. So I'm just going to quickly get to the end, just because there's a map. So that's the entire map it builds at the end, and that's a GNSS solution in comparison to it. Now, one of the main things in, for example, open pit mining is, you've got a great clear sky, you've got great GNSS solution. Do we even need these methods? Well, if you've got loss of RTK corrections, or you go under gantry, or anything where you lose those corrections, you don't want your vehicles to just stop. You want them to continue operating. And that's where these intermediate solutions will come in. And specifically in the tasks of mapping, where you're trying to build a map of the environment, any errors in the GNSS post solution carry on to that. So can you, fuse a GNSS solution with your solution and get a better estimate? Now for a very, very different application, we did a handheld LiDAR at Mount Cootha at one of the trails. And this wasn't me, this was one of the thesis students who needed some data. I was like, sure, I'll take the data. So that's what the data looks like. Just raw scans. It's very shaky. The student was probably holding a laptop in one hand, the LiDAR in the other, and walking around this track. And we can just about make out, there's a tree there, the path's there. And if we go ahead and run SiMpLE on that algorithm, we can see that the trees start to form. So we can start making a very dense map in that environment. Now, once again, same algorithm, same parameters, it's working, and that's what we want. Once again, this might be an environment where you actually might not get GNSS solutions, which is why we couldn't compare it to a truth. But the map and overlaying it on top of Google Maps helped validate that this was indeed working. So that goes on for a while, I'm just going to skip that. But once again, very different environment. And the question that gets raised is, okay, where does this go on now? So we provide a front-end LiDAR odometry solution only. And the solution works well, but like I said earlier, a single incorrect estimate and everything's off. And the data sets we've tested with have had full scans, nothing's gone wrong there, but it's very likely that when you implement this in a machine that's operating 24/7, something will go wrong. And you don't want your robot to be driving off a cliff. So it's going to be ideal if we attach this onto a back-end solution. And there's many out there that are wonderful and great. The only thing is they come at the expense of adding more configuration parameters. So maybe there's work to do there as well. We can also improve the solution of our own result. So like I said, addition of a backend, incremental smoothing, where we don't actually have loop closure, which is what a lot of these backend solutions rely on. Sensor fusion with other modalities. So you've got IMUs, you've got cameras as well. You can add redundancy in there. And many of the existing algorithms do this. We just wanted to see what we could get out of a point cloud and get that to work. You could also have inclusion of a process model with filtering methods. Once again, all in the attempt to reduce errors coming into the solution. And then the question gets asked, okay, we can provide a trajectory that has heaps of solutions in its own, heaps of applications in its own. We also produce a map. What applications does it actually have, and where can that be used? The other exciting thing is they've got new sensors coming out that provide more information. So a major downside of point cloud to point cloud registration or scan matching is you require features. If I go into a tunnel environment, it thinks it's not moving. Even though the car would be speeding up at 100 kilometers an hour, it brakes. Okay? And that's just, by the nature of the algorithm, it requires geometric features to go off, which is why it works great In urban environments or in forest environments, it's got stuff that it can match. In a tunnel, it will break. On a long open road, it will probably break as well. These sensors have started to provide per point velocity as part of hardware. So instead of only receiving range measurements of specified heading and bearing and elevation angles, you actually get how fast that point's moving towards the sensor. And this has opened a whole new set of possibilities. Can we use this information along with SiMpLE to go ahead and map environments such as tunnels? Can we improve our own estimates based on this information? It's a whole new dimension of information we're being provided with. So in this example here, this is going down quite a featureless environment at -20 meters per second. So that's the point velocity towards the sensor. But that's some of the exciting stuff that's still happening. And that's it. Thanks, everyone. Are there any questions? No? We're good? Cool.
Well, thanks for that one. Nice and enlightening. Always good to hear through all of these. As a token of appreciation, we do have a mug here for you.
Oh, thank you. Wonderful branded. Thank you.
So yeah, thanks for that talk. I'm sure we had some people enjoy. Definitely had no one with questions at this point.
Happy to flick through to any slides if there's anything. Yes, Alon?
You mentioned the very minimal configuration parameters, but there are a couple, right?
For our case?
For your
Yeah, sure. Let me flick back to it.
Those configuration parameters, are they more based on which sensor you're using or what environment?
No, so we'll talk through one of these at a time. So RNU is a spatial subsample. The entire goal there is just to reduce the size of the point cloud. Okay, and you can go ahead and use any of those voxel grid approaches that are very commonly used. We tend to use spatial subsample. It is a bit slower, but it retains structure of the environment much better. At least that's what we've found. So that's one parameter. Got nothing to do with the sensor, other than how many points are coming in. I'll flick to here. This is our map. So that's just the map we're creating in the background. Once again, we don't want every single point possible. It affects the registration and memory requirements as well. So that's just a spatial subsample. Once again, you can make that the same as RNU, but we tend to make RNU much smaller than our map, just for the registration purpose. ETOL is a convergence tolerance. We've got to stop the searching algorithm somewhere. It's never going to know it's found the exact solution. So that's just a convergence tolerance. And the only one that's really being affected by your sensor your point cloud characteristics is your sigma reward. Once again, not very sensitive, but if you've got this very low density point cloud, we tend to change it slightly and achieve better results. So we've only really got one configuration parameter, which would be your sigma reward, which affects accuracy. The others are there for computation benefit only, which is obviously a huge requirement as well. Because you want fast results. Yep. Yep.
What algorithm do you use to actually register the input scan to the map?
So that's, once again, this one. So we were just...
That's the objective function.
Oh, yeah, so like...
The optimization function.
So you can go ahead and use any search algorithm there is. We've gone ahead and you can use any gradient-based methods, particle filter-based methods. They all work.
Which one did you use?
We used a gradient-based method.
Gradient-based.
Yeah, but purely because of speed. Particle filter is a bit slower, but particle filter does have the benefit that you can put it on a GPU, whereas it's harder for gradient-based algorithms to do that. Yeah, sorry, you had a question? Yeah.
Is the reward-based SLAM, does that only work for LiDARs, or can you also do other like visual-based?
To be honest, I haven't even looked at Visual SLAM yet. I've got no clue how they're even working. But I know that ICP is also prevalent there. So if it's got an application in the VSLAM or Visual SLAM area, I'm sure we could replace some of them with reward-based metrics and see if the same case exists. But yeah. Anything else? No, we're good?
Sounds
Good.
like everyone's happy.
Cool.
All right. Well, that'll wrap up the talk for this evening. We should have pizza arriving not too long from now, out in the hall as we usually tend to have it. Otherwise, that's us done. Feel free. I'm sure you'll be
Oh,
around a
happy
little
to do
bit.
any questions, yep.
Yep. So yeah, otherwise we've got Micromouse coming up in December. That's our only other event so far this year. Other than that, this is us done before exams and stuff, so have fun with all of those. I absolutely won't. But yeah, enjoy the rest of your evenings, and that's a wrap from us.
Thank you.